All right. Can you guys see my screen, folks?
Yeah.
Okay. So I just want to say hello to all of you. Thank you for your spending time over this weekend with us. Uh, Many of you know me, but still, my name is Yogesh Kumar, and I am the lead and president at the Competitive Kids STEM. What we are trying to do now is to promote science, more so in Canada. Uh, and we are trying to bring this contest called Vanda Science Contest. And we want to make sure that you guys are able to participate. And for participating, one of my understanding is that, you guys need to learn, right? If you don't catch up on the science concept and you go directly to the science contest, you may not do that as well as you would expect to do, right? So at least we'll try to cover a few things. And I have been sharing some material with some of you who are interested in participating. I have some material. You can message me directly and I can send you some more material which is not covered in here. I can share more details with you. But there is a lot of things we already have for you to get ready, right? So I want to explain to you what you already have, and so that you can try it. There are multiple things that you could do here. First, there are brilliant courses. These courses are brilliant, so you can get access to the brilliant science courses. There are, I believe, 9 or 10 different courses. When you sign up for the course, you request for the access, you'll get the link which will for that science course. Once you go in there are 8 or 9 different science courses you can get access to. Not You may not be able to use all 9, 10 depending upon your grade. If you're in grade 4 and 5, you may be able to only use maybe 1 or 2 courses, but those are beautiful courses. The one of the course I highly recommend everyone to try is the course which is physics for every day. They talk about how refrigerator works, how science behind refrigerator. So there are a lot of those kind of things you can get through this course in Brilliant. Go ahead, Katrina. What's your question?
It's because I tried Brilliant, and for some of the courses, like it let me do like until I finished 8% of the course, and then
Yeah.
I need to pay.
No, I think what you need to do, I think that I've reported to them as well, Brilliant. If you go back and try again, it'll work fine. You refresh the page, and Ansh has been doing that. He told me that issue as well. So it will work. You just need to go back, and then start again. It'll work fine. Once you finish a unit, it kind of says that, oh, you need to pay, but you don't need to. It's a little bit of inconvenience, I understand, but just go back and try again, and it'll work fine. Okay.
Thank you.
Okay. So that's one. This is brilliant resource. I mean, brilliant is brilliant. I mean, I wish I had it when I was a kid. While you have it, use it. Okay. And with that, I can also tell you we are doing our our math summer contest, CK STEM contest. So Brilliant has also offered us account for the winners. So whoever is going to get the gold medal in our contest will get the free 1-year membership for Brilliant. So that's the amazing thing. So you need to work hard and get the gold, and you'll get the free membership for entire year. Whoever gets the gold for CK STEM contest, not the Vanda. Vanda is different. Okay. So, and then you have a lot of material here. Practice tests. You could try practice tests. I put together a number of preparation material. There's a lot of reading material you can read, and books and things like that. Really good books. Then you also, whatever we are doing today. So last week assignment is here. So if you go in here, so what we did last week, and somebody posted me that they couldn't access the link, I'll check, but it should work. But in any case, I'll figure it out. So you can access that whole recording. And I also post the lesson which was used for this. I will post both of these things. And then you also add extra quiz for you to practice. If you learned something and you want to practice this, then there's extra quizzes. There are 2 quizzes that you could try. So if you haven't tried, if you're learning something and then you apply that learning to solve the problem, whatever you learn will become more permanent in your memory. So that's one thing, that whatever session we do, you will see some quiz attached to that, so you could practice. And we are going to have the session every other week, roughly. And then we also running mini contest, and this is what all the volunteers, there are 11 or 12 volunteers are helping me. And these are for middle school and high school both. And for elementary kids, I'm so sorry, we don't have too much time to put everything together. We are already stretched too much, but at least whoever is asking me, I'm giving you the content you could do, have to prepare yourself. But we are trying to enter so many questions. We are going to put like few thousand questions in the system. And I'm not putting more because hardly anybody has done it, I won't click on it. There are very, very few, 5 or 6 kids has done it. Somebody called Akash. He is the leader. So we are running the leaderboard too. If you go to the leaderboard, you could see the leaderboard. I'm not in the leaderboard yet, but you guys can see if you are in the leaderboard or not. As you do the quizzes, you get the points, and points makes you leader. Next time onward, I'll start talking about who is leading. So you can try this for middle school and high school. If you go back, there are lots of quizzes. As you could see, the quizzes are distributed into the different aspect of the science. This is physics, chemistry, biology, energy, earth and space science. Similarly, we had the similar thing for the middle school too. So you could try these quizzes. And my plan is to release these as well every other week or so. But if you do it, then I'll release. Otherwise, there's no point in keep putting something. We have to do a lot of hard work to put it. So your energy, your hard work will decide if you put more or not. And then we are also putting these lessons. Lesson 1, 2, 3, 4. I have prepared more. I haven't posted it. I'm going to post more. So till lesson 6 is still not complete. I'm going to post more in it. So you're posting all these things. And if you click on any of these, solar system, earth science, simple machines, what you're going to see inside that, a lot of things, you can learn from it. There are some lessons start at grade 2 to 4. And as you keep going, they get harder, and this is distributed in 2 parts because there are some things in here, grade 2 to 5. And if you go back and forces and motion, then, that becomes a part 2 of it, which has more advanced stuff. So there is so much in the course for you to try all these quizzes. There are more quizzes too. These are all the lessons. If you do, each lesson could be like 40-45 minute long lesson for you. You could really learn. If you already know, that's great. If you want to catch up on some of these content, these things, you could definitely try. These are very, very good material, and then there are more questions if you want to practice on grade 6 to 8, grade 1 to 4. There's a lot of material is there. But I think that, as I was saying in the past too, there would be a lot of material. There's no end of thing that you could do. If you want to do, there is another science, earth science course that I have put in, that you could just focus on earth science. You can learn about earth science. Like another course in biology, I could put that together, that we were teaching for the high school student last year. We can open it up for you too. You could try. But important thing is that, just like math, I know like many of you spend so much of time on math. You can do math like 3 hours a day. Just make a schedule, spend half an hour, 45 minutes, 1 hour, whatever works in your schedule. Do it every day, a little bit every day. A little bit every day will make you stronger, right? And even with these mini practice questions, the first time when you're going to see the question, you may get wrong. No problem. Keep trying it, right? Slowly, your memory will start building up. And that's why some of these quizzes have unlimited attempts. You can attempt it as many times. You could see nobody in high school has even attempted even a single time. So, and middle school, at least few guys did. So if you do more, you will see more. Okay. Any questions so far? I want to stop. I want to focus on the topic today. But again, just remember, you have brilliant. You have these, whatever session we are doing, there'll be quizzes for those one. You can practice that. Then middle school and high school, more quizzes, then more material to do. So much more. Yeah, go ahead, Chris, if you have a question.
Yeah, I just had a quick comment. I don't think the course is really nice, but I don't think the leaderboard works.
Oh,
It says like admin and then two.
No, leaderboard will work. I can see the report. People who has done the assignment. Leaderboard only works, right? Let me explain to you. Leaderboard is only for these 2 things, because these are the mini contest. So leaderboard is tied to these. So if you do these quizzes, you will see your score on. For anything else you do, you won't see on the leaderboard, because other things are for practice. These is more like a contest. Make sense?
Okay.
So you have to, once you do this, you will start appearing on the leaderboard. Okay, any other question, folks? If not, then thank you so much and enjoy the session. I'll be here. I'll be learning with Varun too. And, keep asking questions. Make this session interactive. Okay. You can take it from here, Mr. Varun.
Okay. Hello,
Did I
everyone.
start recording, by the way?
Yes,
Yeah.
it is recording right now.
Yes. All right. Hello,
Yeah.
Mr. Varun.
Okay. Hello, everyone. So I hope you had a good few weeks. Excited to learn today. Because I know I'm excited to teach this lesson here for this weekend. Today, we're going to be talking about, if my screen is going to share. Okay. Yeah. Today, we are going to be working on physical and chemical changes. Ooh. Okay. Is my screen sharing? I just want to make sure.
Yes.
Yes. And just before I keep going, you can still see that.
No.
Can you see a striped dark blue background?
Mm-hmm.
Okay.
If you share your whole window.
Okay, well, that's fine for now. Okay. Well, today we're going to be talking about physical and chemical changes. And so I just wanted to ask you, while we're just looking at these content screen really quickly, what is everyone's understanding on physical and chemical changes? Just a quick question, just anything works from anyone. Just some discussion to start off the class.
I think a physical change, it's when you can sort of see something happen to an object or anything, and it like changes in like its form, maybe its size, or like its physical properties. And a chemical change is something that happens like internally inside like a substance that we might not actually see on the outside until we analyze it a lot closer.
Yeah, does anyone else have any other ideas?
Like a physical change is something that changes the object on its outside. For example, if you change its color, and some physical changes can easily be reversed. For example, if you make an object wet, that's a physical change, but you can dry the object off, so it would be reversible, while chemical changes usually aren't reversible.
Yeah, so these are some good points, and we've touched on the basics here, but of course, we can actually go deeper into that. And so if we're considering physical versus chemical changes, a lot of the things you guys did say were right, but there's more to it than that. So if we go on to the next slide here, just a quick overview, I guess, of it. So physical change is when the matter of an object changes form, but not the chemical identity of it. It's still the same substance at the end of the day. For example, if we look here, melting ice, chopping wood, mixing these marbles and shredding paper, we're changing the form of the physical actual matter rather than changing it chemically. Where we see chemical changes, there's often a new product that is formed. See these different examples here, mixing these vinegar and baking soda, we get fireworks, burning wood, rotting banana. In every situation, it's changing forms. So that's the most basic overview of that. So let's dive in depth first into physical changes more often. So the characteristics of physical changes that we observe include.
Varun, the top of the slide is hiding. So
Oh, the top of the slide.
Yeah, it's just it's better now.
yeah, it's still top is still hiding. So
Well, okay, so that's the zoom bar.
oh, zoom bar, you can hide it actually. You can
Yeah,
click on it. Yeah, it gives you the option to hide it. It's a hide the bar. I think this is the option.
I'm just looking at this now. I'm trying to.
Okay.
There we go.
All right, perfect.
Yeah, just making sure. Okay.
Try it back, I guess.
Yeah, no, I'm just making sure. Sorry about that, guys.
Okay.
Okay. Yes. So with the characteristics that we see here, so one of the key points of this is that no new substances are formed in physical changes. We can see if you look at the picture to the top right, in these cases, there is a change in heat, but there's actually no physical change to the matter itself. Now, a physical change is generally reversible, and so the things can go back to the original forms after. So about what we were saying about irreversibility and that such things, it's actually interchangeable depending on the actual physical change that we're observing. And so the properties of the substance remain the same even if the physical state changes. So you have to think about the properties of the actual substance. So these properties will stay the same, but there are also some things that may change, such as appearance, texture, color, and smell. And so as we talk more about these physical changes further into the lesson, I might ask you about these things, and we can observe whether or not these things are changing and if that actually affects the physical change overall. So if you can see here, referring one more time to the picture to the top right, you can see that there's heat coming in and out of these two different things of ice melting and a fire burning. Let's just have a quick talk about this. So why do you think heat plays a role in physical changes? In essence, what is heat?
Heat
Static energy.
determined by the how much the particles of a substance will be more and more agitated.
Yeah, it's someone said it, I heard in the background, but yeah, that is a good description of kinetic energy. And that is the heat we're referring to here. This energy that we're getting from that's being released or brought into this system that we're talking about, the thing that we're observing the change in, it's this heat that will agitate the molecules, get them all riled up, it'll get them moving, it'll cause bonds and things like that to break or be formed. And in essence, when these things are happening, this is what we could consider a physical change. We could see, for example, in an ice cube, we know that ice, water, steam, or mist, they're all water. It's just that it just depends on how these different molecules are arranged that alters this differentiation.
I think we
We
lost.
can't hear you.
Yeah, he's
You
Yeah.
have between solids,
Yeah.
liquids, and gases, and changed. You
Hey,
see a
Mr.
physical
Varun, we
change.
lost you for a minute. Maybe your connection was bad. Can you
Oh.
repeat for whatever you say for last minute? Yeah.
Oh, okay. So can you guys hear me right?
We cannot
Hello?
hear you.
Yeah, he froze again.
Hello, can you guys hear me now?
We can hear
Yep.
you now. Okay.
Now, okay. Yeah, so I was just saying, so when we have heat that's affecting these different molecules that we're talking about, if you specifically talk about water, if you think about its states in solids, liquids, gases, it's always heat that will be changing it from these things. It breaks the bonds and it changes the arrangement of the molecules, which is what affects these physical changes. So going off of that, you can also get substances disappearing but recovering in physical changes. We'll be getting more into that in a bit. So just moving on for now, we will be talking about reversibility versus irreversibility in physical changes. Just want to make sure I'm still there for everyone, right?
Yes.
Yep.
Yes.
Yes? Okay. So let's talk about reversible changes. So we see a few examples here. So we see the melting of ice, dissolution of sugar, salt and waters, drying of clothes, and sublimation of camphor. That is a quick little thing I do want to talk about. But the thing about these reversible changes is that there's always a way to bring them back to their original states. Melting of ice, you can refreeze it. Dissolution of sugar or salt in water. If you evaporate the water, you still got the sugar or salt left behind. Drying of clothes, obviously everyone always washes their clothes and then you dry them again. Now, sublimation of this chemical is just a more specific example of this. So if you see that white powder kind of there up to the top left, this is created from trees. And when you have this powder, when it goes from a solid form to a gaseous form, that is what you call sublimation. And obviously we were talking about temperature, and it's due to temperature. So if you had to increase the temperature to make it a solid from a gas, you could reduce the temperature to make it go from a gas to a solid. Did I lose anyone there? Or is my internet all good?
No.
Yeah, still good.
Okay.
We're good.
Good.
Still good.
Yeah. Now, irreversible changes, this is obviously up to whoever's looking at this, observing this. It's just something that you wouldn't be able to change. If you thought to yourself, I need to, let's say, for example, turn back time to fix this mistake, it's an irreversible change. We look at these things, the tearing of paper, the breaking of a glass, the growth of plants, or the weathering of rocks. These are changes that no matter how hard you try, you will not be able to reverse, but they weren't chemical changes. They were something of the matter that was growing or breaking apart. Obviously, in this case, there's also technically bonds that are broken, but they're not bonds that can be put back together. So this obviously just varies from each situation to another. Now, just talking about a few examples of the physical changes, we have changes in state. Now, going back to what I was talking about with the camphor, we have these things depending on heating and cooling, going from a solid to a liquid to a gas. These words here, you will need to know what each of them mean and what state they're going from to what, and whether they're due to cooling or heating. But just know solid, liquid, gas, if you're heating them up, it'll go up in that order. And if you're cooling them, they'll go down in that order. And so basically, now moving on, we have expansions versus contractions. And so this is also based on temperature, but this is more so within each state rather than changing between them. It's a solid being heated up to expand, but not enough to become a liquid. It's just an expanded solid. It's still considered a solid. It's just expanded. And then, of course, contraction is the opposite of that. Cooling, it would make it cooler. Now, one interesting example of this that you see all the time might be when you're observing cracks in the road or cement or the sidewalks. Does anyone know why that might happen?
Maybe because over time the rain continues hitting the cement, so it slowly wears the cement down and it forms cracks.
Maybe because of erosion.
It stays there, and then like erosion, where it's like it goes into like there are already small cracks, so some normal erosion. Then the water goes in, and then it freezes and expands, and then it like causes a bigger crack, and the cracks keep on getting bigger until the whole thing is broken.
Yeah, that's exactly right. And this happens in a lot of places in nature. That's, I believe it's not weathering. There's a specific type of erosion that it's called. But yeah, when water seeps into something, it freezes, it expands. But when the water melts, that crack is still there, but the water is gone now. So there's less stability. And this happens many, many times over many, many years. And eventually you get cracks that need to be filled, or it causes things to break. And a lot of the time, if you see cliffs falling and such, like in like Iceland or something like that, when you see the big rocky cliffs, if they're breaking apart, it's usually due to the expansion and contraction of water. Now, just quickly talking about crystallization, this is more a specific example of when you have different solutions and you get a pure crystal of these substances. So the crystal is just a definite geometrical shape of the solid substance that you get. And so if you wanted any examples, it would be kind of like having a solution. So that would be like water mixed with some sort of solid that dissociated into it, which I will be touching on right after this. That basically means the substance kind of just mixed into the water in its molecular forms. And when you have this water being evaporated and this the solid that is right now aqueous, which means it's mixed with the water drying, you get these crystals. And what you see is that it's just these molecules in specific arrangements. If you want to talk about crystallization or ice.
You're getting frozen.
Did we
Yeah,
lose
you cut
him?
out again.
Mm-hmm.
Yeah, you're cutting out.
Yeah, I'll be back again. But if you guys have any question, you can ask, or you can discuss among yourself too.
Some sort of solvent, which means
Yeah, so we disappeared for quite some time, for a minute.
oh,
Okay.
Yeah, so I'm not actually like home right now, so I don't know what's going on with my internet. Okay. Where
Glitchy.
And you cut out again.
Hey, so Varun, I would suggest you one thing when you come back.
Maybe turn off your camera.
Yeah, turn off the camera. That'll save his bandwidth. Well, we need to get him back. But okay, let's see if he comes back. But any questions, folks, so far?
No.
Okay, so far the easiest stuff. You want the harder stuff?
I understand it so far.
Okay.
I understand.
Oh, this was the intro so far.
Here you
Okay,
go.
Varun, are you there? Just give me 1 sec. I'll try to call him.
I'm terribly sorry, everyone.
Yeah, put your
Internet.
camera off, Varun. Okay, that will, that'll help.
Just turn off the camera. Maybe it'll help.
Yeah, that'll help. Yeah.
Okay, yeah. Sorry about that, everyone.
Yeah.
Let me reshare my screen here. Okay, there we go. Everyone can see my screen. So, sorry about that. Where did I cut off?
You're talking about crystallization.
Yeah.
Okay.
We
Yeah,
could
so-
go to the next slide. It's fine. I think you could cover.
Yeah, I was just
Yeah.
going on to talk about just a little bit about dissolution,
Sure.
where you get solids that are dissolving into water and they're breaking down into their molecular forms. So this would be like if you drop table salt into water, it would dissociate and dissolve as two different molecules. So just a quick question, what is table salt made of? Just like the basic one that everyone knows of, the chemical compound.
Sodium chloride.
Yeah, NaCl, sodium chloride. And so when you mix this into water, it would actually mix up in Na and Cl bunches. It would be free floating throughout the water, and that's what you call dissociation and dissolution. So now we'll be moving into a few examples here. So just a bit of practice. So which of the following changes are physical irreversible changes?
Yeah,
Does anyone?
and folks, I mean, I have made, you can send it to host or send directly to Varun, please, if you want to send your answers.
Oh yeah, go ahead. Okay, I got one answer here. See if we get a few more.
Yeah, Katrina, send it to Varun directly though.
Yeah, yeah.
His name is Varun. I'll send. Okay.
Yeah, okay, so I have a lot of answers. I have a lot of answers here that are saying C for the first one and D for the second one. Yeah, and so if you said C and D, then you would be correct actually. So I do see a few people saying B or D for one. And obviously, I just want to quickly go over that because it's nothing to be like afraid of or anything. You are giving your best shot on this answer, and that's what we're here for right now. So I just want to quickly explain. So if you melt something, that is a change in state. Obviously, you could refreeze it. It might not be the exact same shape as it was before, but you have to consider that it's still the same ice cream through and through. Even if it's melted or it's just completely frozen solid, it's still that same amount of ice cream. And if you melt it again and freeze it again, it's still that ice cream down to a molecular form. And also, if you dissolve just normal salt into water, obviously, if you evaporate the water, which is what I was talking about, I could have been disconnected. I don't know though, but yeah, if I was disconnected, I'm sorry. But yeah, if you dissolve this something into water and then evaporate it, you will be left over with your solid from before. So for one, yes, breaking of a glass tumbler, that was one of the examples in the slides. And for two, which of the following is a reversible change, obviously A, B, C, you couldn't undo it by yourself, grinding a wheat, you grinded something down to powder, shredding a paper, you shredded it down, chopped it all up. How do you unchop it? How do you unshred it? How do you ungrind it? You can't. So even just without knowing what a physical reversible change is, you could know through the process of elimination that you would get D for the second one. Are there any questions about this?
No.
No.
Pretty straightforward for this one. So let's go to another example here. So which of the following represents a physical change? Nothing about reversible or unreversible, just which one of these represents a physical change.
B.
Okay,
D.
I'm just waiting for some answers here as well. Okay, so I will reveal the answer now. It is actually D. It is all of them. So what you have to consider is that you're just changing the physical shape of these. Just because you didn't like melt it or something like that doesn't mean it wasn't a physical change. Making a paper boat, for example, you have changed the shape of the paper. You didn't need to melt it or anything, but it's not the same as it was before. There was a physically observed change to the paper that you're observing. Now, same thing for A and B. Bending an iron rod, it's not the same as it was, and technically you could unbend it. Sure, it might be unstable, unlike before, but technically it was a reversible change. But that actually isn't relevant here. It's just that there was a physical change. And now for anyone who's, if you didn't consider A, and I think some people did say B and C or just B, for A, think about expansion versus contraction. You heat up this iron rod, and sure, it might have not melted into a liquid, but due to this heat, it would have expanded slightly. Right, so is there any questions about this?
No.
Nope, okay.
No.
One more example for physical changes. So, which of the following statements is correct regarding the crystallization of copper sulfate? So, I will be helping us run through this question just in case. And so, what I did wanted to ask is, does anyone know what color copper sulfate might be? I know it's a very specific thing, but I just wanted to see if anyone did actually know.
I believe it's blue.
I think
What's that
someone's
noise?
someone's mic or their internet
Yeah,
is
someone's
lagging.
mic isn't working.
I think
That sounds weird.
C.
It's blue, I believe.
Okay,
Copper sulfate.
yeah.
So guys, instead of
Copper-
telling the answers,
Wait,
you
how
can
do you know
send
copper
send
sulfate?
send it to, sorry, the answer, send it to Varun, so that
Yeah.
others have opportunity to try it out. Don't say it, okay, please. Go ahead with your question. You were asking something.
Sorry, yeah. So blue is correct. Copper sulfate, copper compounds tend to be blue, yes. And so now, what is so important about this color that I was talking about? Of course, it has to do with B. The color of crystals obtained is blue. So you have to know that the actual substance is blue. So of course there'll be questions on the contest that are specific like this, and you might need to know things. And what I will tell you is copper compounds are generally blue. So yes, that means that the color of the crystal obtained will be blue because we are obtaining the substance in its pure form in a crystal. That is the point of crystallization. So it should be, in most cases, the same color as what this solution would be. Now, question A. What does A actually mean? I'm just working through this with everyone so they can get a great idea of these different meanings and the different situations. So what does A actually mean in this scenario? The solution is made super saturated. So we know what a solution is. A solution is obviously a mixture of these different solvents and solvents, and when these are mixed together and they're dissolved, we get solutions. We know that saturation is the amount of something that you dissolve into these solutions. Sorry, can everyone hear me right now?
Yes, we can.
Yes, we
I
can.
can hear, but Ananta, you have the question. You can either send. We can't hear you, so you can send your question, Ananta.
Just message me.
Ananta, you have to send your answer by typing. We can't hear you. So either send it to Mr. Varun or you could send it to me.
Yeah. Yes, right, yes. Ananta, yes.
Hey, can you read the question if you got the question so we all know?
No, she was just confirming. I think they're still sorry. Yes, okay. So now we have an answer from Ananta. It is supersaturated is when you saturate beyond a certain point. So yes, I will reveal to you that is correct. And that certain point is the maximum amount of this substance that you can actually dissolve into the solution. At that point, there's no more of it being dissolved in. It's just kind of going to be sitting there at the bottom. And so that's what it means to be supersaturated.
Mhm.
And so if you're talking about crystallization, when you want to make these crystals, you're going to want to have as much of the substance as possible. So yes, the solution will be made supersaturated. And think about if the process is reversible or not. You're making these crystals. Obviously, you could re-dissolve them back into the solution. And so, as many of you have been saying, the answer is indeed D. So you have to take an approach to these questions systematically, and you have to eliminate these options, and you have to think about it scientifically.
So,
And I know that.
do you have any question? I'm trying to unmute yourself. Do you have any question at this point?
Yeah, any questions, just send them to me or Yogesh.
Okay. If there's no question, you can continue.
Yeah, okay. Oh, I just want to keep the chat open just in case. So someone asked, how do you know it's blue? That would actually just be knowing the different compounds that are going to be used in examples. You'd need to know the actual just color of it yourself. So yeah, I know that is sucks sometimes, but there does happen to be quite a bit of that in chemistry, and it's something that would be good to get used to, and something that will help along the line, depending on what your interests are. So just moving ahead now. So we will be talking about chemical changes now. And so chemical changes are different to the physical changes, where you have these changes that are usually irreversible. And so what we can see from these little pictures at the bottom here is that you usually get one or more new substance that is formed. And this new substance will, in most cases, or all cases for that matter, have different properties than the reactants. So when I say reactants, I'm talking about the things to the left, the things you combine or the things you're breaking down, and the products are the things you end up with. And so now there's one thing we do know about energy is that it can't be created, right? But when I say things like heat and light and sound produced, what does this actually mean for chemical reactions? Ananta says yes, you can test your mic really quickly if you want to
Can you
answer
hear
this
this?
question. Yes, we
Yes, we
can.
can.
Okay.
Yes.
Okay. Yeah. So this question. So yeah, sorry. Go ahead.
Eh?
Yeah, were you going to answer the question?
Testing my mic.
Oh, okay. Yeah, no, I was just asking. So heat, light, or sound is produced. That's what this book says. And so that's what these slides say as well. So what do I actually mean when heat, light, or sound is produced?
It means that from another source of energy.
With light bulbs.
Heat, light, or sound is created.
Like
Yeah.
if heat
It
is
gets transferred.
Yeah, you don't ever create energy. It is a transition of energy, it is a conversion of energy from one form to another. Whoever said a light bulb, what is the basis of a light bulb? It's actually electrical energy being turned into light
and
energy
heat.
and heat energy as well. Older light bulbs created a lot of heat that are less efficient, but that is the story for another day. Basically, you are turning different forms of energy into others using different reactions. And so these chemical changes are referred to as chemical reactions. If we look at the bottom left picture, you see all these different things. Eating food is just a chemical reaction. You're breaking down the food and turning it into energy for your body to use. So things like that. There's energy all over the place, and we're always transforming it and changing it. And that is why chemical reactions are so important. So are there any questions just related to this?
I don't have any questions.
Yeah, just put them into the chat if you have them. I can always go back if I need to. So now we're going to be talking about the characteristics of the reactions that are seen. So one usual consideration that you've seen a chemical reaction is that you have a gas that is being released. Usually gas will occur from a liquid solutions of reactants. So you'll have liquids or aqueous solutions. So aqueous means that there's a solid dissolved into water or some sort of solvent. Liquid, gas, solid, those will be denoted for you in these chemical reactions. Like it'll tell you what kind of thing it is. So one thing to look for is gas. You'll see bubbles, and these arrows that you see, like look at this first example up at the top. Carbon dioxide is a gas, and that is what's creating the bubbles. And so for the competitions pertaining to this Olympiad, you will see that there will be an up arrow denoting that these are in the form of bubbles. Moving on, you have products that may be a different color than the reactants. If you mixed up this zinc and this copper sulfate, the copper sulfate, which we said is blue, and zinc, which is generally just, I believe, just a metal, or it could be white if it's in a powder form, we get the zinc sulfate solution, which is white, and you get the copper metal, which is like the copper color, like kind of like the bronze, like, yeah, the shiny,
Brownish.
yeah. Now, another really big thing of chemical reactions is precipitate, and precipitate, either way, it's a solid product that's separated from the solution in the middle of the reaction. This one sort of solid isn't able to dissolve back into the solution, so it's denoted by a down arrow, and it's just a sort of solid sitting there at the bottom of your solution due to your reaction. And now this is a very important bit to this. Exothermic versus endothermic reactions. And now, I accidentally scrolled up a lot here. And so one thing to consider greatly in endothermic versus exothermic reactions is how you're considering your heat energy is being used. Does anyone have an idea as to what exo means and what endo means?
Exo means it like emits heat, and then endo
Exo
means
means
it takes heat.
outside, endo means like inside.
No,
Like,
exo means
exoskeleton is like
external. So heat produced. Endo means it requires heat.
Yeah,
like
so
an exoskeleton.
One thing I request you guys to do is to not talk over each other. You can raise your hand and we can call your name, okay?
Yeah.
Yeah.
So yeah, you guys are right. Exo, I was just referring to the startings. I wasn't referring to the energy yet, but yes, exo. So sorry about that. Exothermic is releasing, and endo is gaining, absorbing. So yeah, just exo outside, endo inside. So when you add the thermic, you're specifically talking about the heat. And so exothermic means that heat has been released due to this reaction, and endothermic means that heat needs to be absorbed for this reaction to occur. Right? So when we were talking about heat earlier, we were talking about how it makes or breaks bonds. You need energy to break these bonds, to overcome the things that hold these bonds together. And so if you consider an exothermic reaction where you are releasing heat, you will actually have bonds that are formed because you have less energy, and therefore more bonds have been formed. So is there any questions pertaining to this?
I don't have any questions.
Yeah. And sorry, I just realized I just said that the other way. You need the heat energy to actually form the bonds, because the bonds will be at a higher energy than your just your normal substances. And so if you just look at the reactions in the bottom right, the bottom one would be endothermic, where you have heat being absorbed into the reaction to make the bonds. And in the top one, you have heat being released as a product of breaking bonds. And obviously
So-
last we have, oh, sorry. Yeah, what was that?
So when we're like breaking bonds, heat is released, and when we're trying to combine bonds, heat has to be added.
Yes, that will be your major explanation towards if the reaction is exothermic or endothermic. Yeah, so it just depends on where the heat is actually added into your reactions. So the one last thing though is the change of states, and we were talking about this earlier. And this this pertains to whether you're in a solid, liquid, or gas. I know we were talking about that in terms of physical changes, but you also need to talk about it in terms of chemical changes, because the evolution of heat, which is what you call when heat is lost or gained in a reaction, changes the actual state of this. So let's run through a few examples here. I just want this list that we have of physical or chemical changes to be sorted. Just yeah, send me the different things, or we can go one by one.
Yeah, I mean,
Yogesh,
or
which
what
do
you could do,
prefer?
you could write on a piece of paper and segregate which 1, 2, 3, 4, 5, 6, which one are
Yeah,
or
yeah,
chemical. Yeah. And
I
then,
say we just wait here for a minute
yeah,
or two and
right.
just write down which number you think is which. So just say 1, 3, 5, 7, 9, whatever is physical, and the rest are chemical, something like that. It's just to get everyone thinking about what we've been talking about. And I will show the answers after.
You don't have to do all 18, just try as much as you can. It's kind of pretty mixed up. The idea is that you are able to differentiate what's physical versus chemical. If there are any doubts, will be clarified on the next slide.
I just put like a P for physical, C for chemical.
Yeah, that's fine.
Okay.
So I'll just give it another minute here, and then I'll move on to the next slide, so we can just keep it moving, and we'll just give everyone the basic rundown when we get there.
Yeah, you guys done now? Can we move on?
No, could I have like 30 more seconds, please?
Okay.
Yeah, sure, go ahead.
Thank you.
Okay, so even if you're not done, that's perfectly fine. We just want to get a good idea of this, and someone actually sent a full list. You can check right now if that was correct or not. So here we see that the physical changes versus the chemical changes, and actually wait, I don't.
Last one is missing because it's different. So we have the explanation for that in the next slide. Yeah.
Yeah.
Because these are neither chemical or physical.
Yeah, so if we just
Uh,
quickly go back here, salt mixing in with water, and then we'll go back to here, so we can see that that is actually missing here. So physical changes we see in every single situation, that it's something that we can observe. It's something that either we consider to be irreversible. Well, the irreversible ones you can tell for the most part that they are physical changes. I guess reversible ones is where it gets a bit different. But yeah, generally, if you talk about state changes, even though it is a chemical change, you consider them physical changes because they're easily reversed and such things like that.
So
But yeah,
any particular one, like some of you really thought, oh, how come that's wrong? Okay. Anyone that jumped out at you and said that, okay, that why something is in that category, it should have been another category.
yeah.
For me, it was the one where it said carbon changing from graphite into a diamond.
Yeah, that one's surprising for me too.
For me, I don't really get why evaporating alcohol is in physical changes.
Okay, so this kind of has to do with this has to do a lot with the kind of physical changes that we see. Well, we'll start with evaporating alcohol. If you evaporate something, you are changing its state from a liquid to a gas, kind of like if you're just boiling water, you are evaporating the water. And if you were to collect these droplets and this gas of the alcohol or water for that case, you could actually cool it back down to convert it back to a liquid alcohol or liquid water. Yeah, okay. And I just want to just quickly talk about someone's message in the chat. I'll get to the carbon at the end. So precipitate forms, this would be a chemical change because a precipitate wouldn't form unless a new substance is actually produced, which we said is a key factor in chemical reactions or changes. There actually has to be a new substance that is formed from the reactants, a new product that is found, and this would be a precipitate, which is a mixture of probably two of the atoms or molecules in the reactants that become a product that just doesn't dissolve well with the prior solution. And so it's just kind of chilling there at the bottom of the reaction. It was formed new. It wasn't changed. It wasn't the change of a state of one specific substance. And now that segues us perfectly into the carbon changing from graphite into a diamond. If you've heard about the thing of people turning coal into diamonds, that's essentially true for the most part. Coal and diamonds are both just carbon. The only difference between them is how compact this carbon is and how dense it is and how it is cut and shaped. Pressure is what molds these graphite into a diamond, and so it is not anything being added to the carbon. In its basic form, it is still carbon, and therefore it is actually just a physical change. There is no chemical change going into this. Does that answer your question?
Yeah.
Okay. Yeah, and
It looks like, you take the water, make it ice, and you cut the ice to make shapes out of it, beautiful shapes. You go to some ice palace and you see these ice shapes. So now it's a physical changes. I mean, it's still the water. If you, increase the temperature, it'll come down to everything will
Yeah.
down to water again.
Now,
but-
if you had to add, let's say, some random metal, like just say you had to add some copper to turn graphite into a diamond, well, then it would be a chemical change because then
Yeah.
the diamond would be its own different substance. So let's just move on here. And we're talking about this. I know chemical and physical changes, it does get confusing. We just found that out. So in some cases, it's just hard to tell. Like for example, especially when you're dissolving things, there's physical changes that occur. We see the solution changes and such like that. And so if you want to consider sugar versus salt in water, you have differences in the chemistry of these reactions. And sure, in both of them, it kind of looks like there's a physical change. But in one or the other, there may or may not be a chemical change. For example, sugar, which is made up of mostly sucrose, it wouldn't exactly break down in the water. It kind of just dissolves in. Whereas salt would dissociate into its ions. This is what I was talking about when I was talking about dissociation and dissolution, is when you have this compound dissolving in the water, it actually breaks down into its ionic forms. And so you have a chemical change that's actually occurring because you have new products. And therefore, in either case that you see it in, there's a gray area in the chemical changes and the physical changes. You could almost be considered both, but it rides a very fine line. And so we know that just this one sentence here at the bottom line perfectly sums it up. If it has every sign of a physical change, it can be produced by a physical change. But that doesn't mean a chemical reaction has or hasn't occurred. The only way you can check that is by running analysis of your reactants versus your products. You have to know if something new was formed or if something wasn't formed. That's where you run into problems. And if you keep that in mind, I bet you it'll help you out in a lot of the tough questions, kind of like the ones we're just working through. Just because it's in a different form doesn't mean it's a completely new material. So are there any questions about that directly?
No.
Okay.
Nope.
So we have a bunch of questions. We could go a little faster, though, Varun.
Yeah, sure, go ahead. So now I just want to talk about the few types of reactions. I kind of had this on the slide back here. Let's just talk about synthesis reactions and decomposition reactions. So we can see the basic chemical formula and the changes. So this is also called a combination reaction. It's just when you have two different products that are or two different reactants that are combined into one product. So sometimes if we're talking about how you need to create a bond, therefore it may require extra energy in the form of heat, light, or electricity. And so there's a quick example here where you see magnesium is reacted with oxygen and you get magnesium oxide. A decomposition reaction is the opposite to the synthesis reaction. It's where you would be breaking down this one product that is made up of two different elements into its basic forms. And so in this case, you would need energy. You would need energy provided to break the reactions. And so rather than releasing energy, you would be absorbing it. And so there's another example here where you see heat is used to break the actual bonds. And sorry, when I was talking about the first one, it's more to precede the reaction rather than actually create or change the bonds. So now this does get a bit more different here. So this is a displacement reaction. This is when you have an element with another compound that's turned into a different compound plus a different element. And so this depends on reactivity of elements and such, and that varies from different compounds depending on what the solvents you used. And so there's a quick example here where you have iron and copper sulfate in the solutions being reacted, and what you can see in that bottom reaction there, where you have the iron plus the copper sulfate, it becomes iron sulfate plus copper. You basically switch the metals there to the different ion. Now, another very important thing that we can consider here is rusting. Rust is the reaction of iron, oxygen, water. It's basically whenever you have steel, or not steel, but iron sort of in the air and it has moisture on it, which would be the water, you get rust. And so there's preventions of rusting. So to proceed the reaction of rusting, you actually need access to oxygen and water. And so if you were to paint the surface or grease the surface, water wouldn't be able to get in. You wouldn't get moisture, and therefore you wouldn't be able to get, you wouldn't be able to get any rust because your reaction wouldn't proceed there. And there's also this method called galvanization, and that's a process of coating the iron with zinc, and basically that allows it so, again, the iron just doesn't get access to oxygen and water to rust. So there's many of these smart solutions to these different problems that we consider based on the chemical reaction of things. And now moving on, you get usually one of the more confusing types of reactions. It's called a double displacement reaction. So this is where you get a lot of compounds that are mixed together with other compounds. And basically what you'd see is in this reaction is usually it's just a switch in the second bit. The second bit of the compound is what would switch between the two, and that would give you two different things. So the types of double displacement reactions, you get precipitation reactions, where you get solutions that create a precipitate, which is insoluble, which is what I was saying. It kind of just goes and sits at the bottom. We talked about this last week. You get neutralization reactions, where you get an acid plus a base becomes salt and water. And then a very important one, you'd also, this is different from double displacement reaction. You get oxidation and reduction reactions. So this is adding or removing oxygen or hydrogen. Sorry, you add oxygen or remove hydrogen, that is oxidation or oxidation. And if you add hydrogen or remove oxygen, that is a reduction reaction. So moving into some practice here. So we were just talking about rusting. So just send your messages in the chat for this one. It's a quick one. Rusting will occur in the presence of what? There's some sort of metal that rusts, and what is it? Give it another 5 seconds because everyone should be getting this one. Yeah, perfect. The answer is B, oxygen and water required to rust. So which of the following represents a displacement reaction? Where you see something is displaced. You have you have one element and a compound, and it switches. Okay, just a few more seconds here. Okay, so for question 2, a lot of people were saying A and D. Now, if you're actually considering the natures of rusting, specifically in this case, is rusting a displacement reaction that you see in nature? You have iron, you have oxygen, and then of course you have H2O. And then you get the O from both of them going into the iron, and you get your iron oxide. But in definition, this is not actually its own displacement reaction. If you want to talk about a displacement reaction, you should be focusing on the compounds in the reaction. So iron nails that would be kept in a copper sulfate solution. We've been talking about copper sulfate quite a bit. Copper sulfate is a compound. It's CuSO4. Sulfate is SO4. Cu is copper. When you actually have this iron nail kept in this copper sulfate solution, what you'd be left with would be iron sulfate and leftover copper. It would switch. You get a displacement in the irons, in the metals for the non-metal. And the last question here, for 3, we would get, I don't know if, I think a few people did answer this as well for 3. We got, okay, so we know if you heat something up, you could cool it down. If you evaporate something, you can, once again, cool it down to bring it back to its liquid form. And sublimation is a state change, and a state change is reversible in nature, depending on the temperature. And so you'd have to consider curdling, because I mean, if milk goes bad, if you can make it not go bad, then we would have a lot less problems with expired milk, wouldn't we? But no, that's not the case. Curdling is not reversible in nature. Maybe like in some high-tech lab, it would be, but not just for normal people. But if we did have, for some reason, the sublimation of iodine into your houses, if you just cooled it down, you would get your solid iodine again, or liquid, I guess. No, solid. So are there any questions pertaining to these? I know it is just a bit confusing to be thrown into the deep end here for that, but I think it does help because these kind of scenarios are just for learning.
So are you guys enjoying the session so far?
Yeah.
Yep.
Good. I like so many yes. I'm excited. Okay, let's keep going.
Yeah.
Well,
Yeah, so now we can work through this together. So in the synthesis of biogas, which is obviously just fuel that would be made from biological materials, you get organic waste collected in a large pit, organic waste, whatever, rotting tree roots, dead animals, that kind of things like that, organic waste. Then you get anaerobic bacteria. If you guys have been keeping up with your biology, I won't ask you what it means, but anaerobic bacteria would be bacteria that doesn't need oxygen. It would convert this waste into biogas because it would consume it and then produce the biogas. That's the first process. Then this biogas is supplied to homes where it is used as a fuel. So process 1 and process 2 are what each? You see, okay.
Yeah, does anybody have the example of biogas? What is biogas? If you know any real life examples? Nobody knows?
Any cool examples of biogas? Anyone have any random burning passion for biogas?
Yeah. Okay, so nobody. Yeah, so we want to talk about a little bit what is which country and where it gets more used. Maybe that'll help them.
Yeah, I guess. I don't know exactly what country it might be used a lot in, but if it's produced from organic materials that maybe are waste. If you think about waste in biology, well, what do you think animals and such produce?
True.
Yeah, someone said cow dung gas. Yes, that is a very good example of biogas.
Right, and it's true like that. In India, they
Yeah.
use that to create biogas, to for heating and electricity and all those kind of things.
Yeah, and it's a very good use of their resources. As even if anyone thinks of it disgusting, it's yeah. Someone said methane. Methane is like a byproduct gas. It's not as much as the biogas that they use, because the organic material. Now I'm going to be answering the question. The organic material is broken down into different components where the waste is sorted away from what the biogas actually is. The bacteria is consuming that waste part and leaving behind the biogas. And so that is technically digestion, which means it would be a chemical change. And of course, we know the biogas is then supplied to the home where it is burnt as a fuel. If it is burnt, then you would have obviously carbon being introduced from the flames that are burning it. And if it's burned as a fuel, then you get chemical changes. So if anyone said C, C is the correct answer. So you have to think digestion. The act of digesting something might be physical and chemical, but overall it is chemical. For example, if you just say you eat some good chicken rice, or matar paneer for all the vegetarians, you get you chew it, that would be a physical change, but then you digest it, you break it down, that's a chemical change. And so that's what that bacteria, the anaerobic bacteria, is doing to the waste. And finally, we have our last question here for this example, at least bit. So you look at this specific example here where you got the candle or whatever this is burning with a great light, and then you have a ribbon of magnesium, so just magnesium. So what are X and Y in this scenario? I know might be a bit difficult here.
And for the young kids who are still trying to understand, you get the idea that what the philosophy is behind those chemical and physical changes, even if you don't understand all these chemical equations, but the fundamentals of how these things work, what's physical, what's chemical, you get the idea, right?
Yeah, of course. This question I could have fit into the higher level examples, but
Right.
it's good to just have a basic understanding, if possible, of these different reactions and why such things are occurring.
Right.
Yeah. Do you guys still see the slides right now, or what do you see?
I can
See
see
the
you.
I see the slides.
Okay, good.
So you're not getting any answer, Varun?
No, I did get. I just got a couple answers here. Just waiting to see if anyone else cares to chime in.
Okay. Yeah. So maybe this little, confusing for people. Maybe it's good to get to the explanation of it. Mm.
Yeah. Okay. I think we just have a good bit of answers here. So now in the picture, what we see is the production of X. We get how X is produced, not how Y is produced. Be careful with that. So in this case, of course, we have this candle or whatever that is burning with a dazzling light, and we get this magnesium that's being held around it. And so what is being consumed by a flame to actually keep it running? Oxygen. So we know that there will be oxygen around this flame. And so what we're actually producing here is, while this magnesium is burning, we would actually get MgO. So we know MgO would be our X here. And when you combine this with water, you'd get a synthesis, you get a sort of synthesis reaction here because you don't have two products. It would be MgOH. So anyone who said B is correct. It is a bit of a harder example to understand, and there is some logic that goes into it, but obviously with more practice will come more familiarity with these topics, and you'll be able to get the right answers all the time. But of course, learning is what's the most important thing. So speaking of learning, let's get on to some higher level examples to iron out some understanding in these situations. So we have this entire question here. So during a science activity, Miss Suleika took some sugar in a spatula and heated it on a Bunsen burner. A Bunsen burner is kind of this thing that just has gas flowing through it, so you can light a fire on top of it to use for chemicals. So there's sugar in a spatula, and now they're heating the sugar on a Bunsen burner. Now a black mass was obtained. Then she dissolved some of the sugar in a water in a beaker, and then they heated the beaker using water bad till the white powder is left at the bottom of the beaker. So which of the following is true about 1 and 2? In the chat, just get some ideas flowing.
And if you have a question, you can also send it to Varun, not just the answers.
Yeah, any questions as well. You could also, if you just have a question that you think would be good for the general understanding of the class, you could unmute and ask, but I just want to see if you hear. Okay, we got some answers flowing in. That's good. That's good. Let's get some more. I'm seeing a lot of I want to see some new people answering these questions. Just take a shot at it, because at least then you put some sort of thinking into this. You're participating in this, and that'll actually help you learn more. If you're kind of just I especially notice this in my classes, even this applies everywhere. If you're kind of just passively learning, it won't help you as much as even if you attempted the question and got the
I have a
answer wrong.
question. Like,
Yeah,
can you
what's
choose-
up?
Can you choose a multiple answers or only one?
No, this is a one answer thing. I wouldn't see why you'd have to choose multiple of them, because there's technically none of these option if that's what you think is right.
Okay.
You are thinking about it. If some of you, if you haven't, you don't know why we are doing it, this is for the Vanda science contest, because there's like some of you I know haven't signed up for the contest. So the ultimate goal is that, learning needs to be associated with something meaningful. We just learn for the sake of learning, just there has to be some kind of end goal. And one of our end goal is that we are preparing you for this contest, and we encourage you participate in that. And then we have a lot of awards are available for you to win as well. I mean, beautiful medals and certificates. And I mean, if you do multiple contests, there is honor societies, and there are a lot of different opportunities which is listed. I'm not going to talk about it, but if you haven't signed up, you may consider signing up for the contest as well.
Yeah, okay. So I think we got a lot of answers this time. So I think that's good. Being able to work it out, if not just by yourself. Now, so in the first situation, we see that the sugar is heated up to the point where it is just burnt to a crisp. Okay, it is just burnt beyond belief. Okay, now if you burn something, what is that actually? Is it a chemical change, or is it a physical change?
Chemical.
Chemical.
I think it's a
Chemical.
chemical.
Okay, let's think of it like this. Let's say you cook an egg. If you cook an egg, well, what kind of change is that?
Physical.
Chemical.
But I think what happens if the sugar chemically changes, it turns into a different subject. So it wouldn't be a physical change in this case, it would be more chemical.
Yeah, I just wanted to get you guys talking about it. Yeah, it is indeed. If you cook something, you burn something, it is a chemical change. Right? Okay.
Mhm.
So there's a good understanding of that. I just want to see, because a lot of times in those situations, some people kind of like changing their answer, but you guys were confident with your answer. That's what I like to see. Now, then you see that she dissolved some sugar in a beaker and heated the beaker using the water bath till the white powder is left in the bottom of the beaker. Now, in this case, what actually happens? So there's sugar in the water, and then the water was heated up. So what happened to the water in this case?
It was evaporated.
Yeah,
So it would just be left with the sugar. So it would be a physical
evaporate.
Physical.
Yes, it would be a physical change. So you have to consider the entire scenario for this. And since you have a chemical change in 1 and a physical change in 2, technically that would get rid of A and B. And from there, most cases, for all intents and purposes, none of these is usually a misleading answer. And so even if you didn't know that if the sugar was burnt to a crisp, that you'd end up with charcoal, which is just very cooked up carbon, I believe, then you'd get the answer is C. And a few people did get that. So good for you. But anyone who answered A and B, you were thinking about whether or not process 1 or 2 were chemical and physical changes. Even if you didn't get one of them right, it's important to at least be attempting these questions to get an idea for next time. Because now you know, oh, well, shoot, something was mixed into something, but it was dissolved, and now you're left with the original thing. That's a physical change. So good job, guys. Now we're going to move on to the next question.
With so many choices, the main idea is that you should be really certain about what we are talking about, so that this build you, help you build that kind of understanding towards the topic. Are you really sure?
Yeah, exactly. Okay, I'm getting quite a few answers as well this time. Nice, nice. So a good way to go about this question, just classify everything first as physical or chemical, right? So I think that is the method some people are going for here. So let's just get the easy ones off the board here. So grinding of wheat, we know you grinded something, you wouldn't be able to ungrind it. It would be a physical change. What type of physical change? We'll get back to that.
Irreversible.
Yeah, it would be irreversible, yes. Right now, we're just categorizing them as physical and chemical because that'll give us, it'll probably eliminate some options for us, right? Now, obviously grinding a wheat, it's just obviously irreversible. So that would actually eliminate question A for you guys because that is irreversible. You wouldn't be able to ungrind the wheat. 3, making curd from milk. Curd is actually a chemical process because it requires a sort of bacteria in it that ferments it almost, and that is how you get the curd. So you might be getting closer to the idea here. A few more easy ones. So a charging of a car battery. If you are charging a car battery, that would also be a chemical change. You are turning your electricity or whatever back into, this goes more into how batteries work, but just for you to know, it would actually be ionizing different sort of metals and such so that you'd have charges to move around. Just a simple explanation there. Ripening of fruits, chemical, boiling of water, physical. Crystallization, I think this is where some people tripped up. That would actually be a physical change. There's no change to the actual substance. It's just giving it a different form, right? So I think 7 did trip a few people up. That is a physical. What type of physical change though? Would you be able to drop the copper sulfate back into water and then recrystallize it?
Yes.
Yep.
So that makes it a physical reversible change, right?
Yeah.
And threshing of wheat stalks, I believe that's just like cutting them down. That would be a physical. What type of physical change?
Irreversible.
Irreversible. Yes, that is correct. And so when we boil all of that down, if we want to look at these options really quick, looking at A, 2 is irreversible. So A is off the table. 3, 5, and 7 in are chemical changes. 3 is, 5 is, 7 is not. I think that's where people got B from. C, 1, 6, 7, 1, formation of clouds. Yeah, that is a physical change. That is just a change of state in water and then our air, our like atmosphere and the water.
Boiling
6,
water.
boiling of water is just a change of state. That is what we consider physical and reversible. And 7 is the crystallization of copper sulfate. That would be physical reversible. And so your answer would be C. But just to quickly go over D, 2, 4, and 8 are chemical changes. 2, 4, and 8 only charging of car battery. 2 and 8. I hope people would realize that yes, that is a physical irreversible change because you are cutting or grinding something up. And so we did get a lot of C, and that's good. Yeah, I know for B and A it was a bit confusing, misleading, and well, I don't want to say misleading. It was just a few tricky ones, but it's good that everyone's attempting these questions. And so let's go for one final question, at least for now. We can get to more if we need to, but there are a few processes here that are listed. So we have the rusting of iron, dissolution of ammonium chloride in water, decomposition of calcium carbonate, and the addition of zinc powder to copper sulfate. So which of these processes of the following is incorrect? Watch out for that, incorrect regarding these processes. So remember, endothermic heat is required, exothermic heat is released. Okay, so I've got a few answers here. So I just want to talk about each one. So if anyone answered A, you can type to me what your thought process was. You don't have to say out loud if you don't want to, and I'll just say it to the class. I don't need to say who it is, but I just want to get some thought process, some of your ideas about why these answers might be right. So for A, let's just start with A.
We could talk, folks. I mean, at this point.
Yeah, talk or type. Like if you're not comfortable talking, maybe you're like afraid to share your answer, just type it to me. I'll say it out loud. I'll keep it anonymous. It's perfectly fine.
I tried all the others and they were correct, so I thought it was A.
Okay, so
I chose A because dissolution, dissolving usually is an exothermic process instead of an endothermic. And so that's why I chose A, because that means process 2 would be wrong.
Okay. So we're saying that this is because we think the other ones are going to be correct, or sorry. So we say B, C, and D is correct, and also that the dissolution would actually be an exothermic process.
Yeah.
Okay. So let's just go over this. So just to talk about dissolution. So we were talking about exothermic and endothermic. And so in dissolution, I just want to ask, what's happening in dissolution? You're getting the what of bonds? What's happening to the bonds of this ammonium chloride in the water?
Wait, could you repeat that?
So what's happening to the bonds of the ammonium chloride as it's mixed into the water?
They separate from each other.
Yes, they are separating from each other, right? And so if you have these bonds that are usually stable for this thing, or else if it wasn't stable, it wouldn't be existing normally, right? If you had to break apart this bond, wouldn't it require energy?
Yeah, it would.
It would require energy, right? So in this case of dissolution, I think you would be thinking more of a I think you're thinking more of a displacement reaction rather than dissolution, which is more of a decomposition reaction. Decomposition would be endothermic because you need energy to break the bonds, right? So yeah, like it does get tough trying to differentiate between these different chemical reactions, but you would be breaking the bonds in a dissolution, which would mean that would be endothermic. Okay. So for now, we know at least 2 is correct. And then 3, decomposition is the same thing. You're breaking bonds. So it would be an endothermic reaction. So it is a good line of thinking. It's just getting used to these different types of chemical reactions. So now if someone would like to share their thoughts on B, you don't need to have maybe answered B, or if no one has it, I'm fine to walk through this one as well.
Yeah, I don't really know what any of the words in B mean.
Yeah,
Okay. So process 3 results in the evolution of gas, while process 4 results in change in color of the solution. So what is this asking? So sorry, yeah, did someone have a question?
Yeah, no, I just know that for number 3, since it's decomposition of calcium carbonate, which contains carbon dioxide, it would release carbon dioxide. So at least the first part of B is correct.
And I think for the second one, for number 4, when we have zinc and copper sulfate, I think it changes color. I think the zinc powder becomes white, and the copper becomes like the regular. It becomes like brownish and bronzish color.
Yeah. So you guys are actually both correct. So that's really good. You have to understand that, yeah, when calcium carbonate would break down, you'd be left with CO or CO3, whatever the carbonate is. It would most likely, if it further breaks down, it would be gaseous carbon dioxide. That's a very good thought. So yes, you would get the evolution of gas. So what evolution just means is that there's some sort of change that led to this. There was a chemical change that led to the gas. The gas was evolved. It was evolved from a solid state. So it might have been a solid before, and now it has evolved into a gas. Okay, so that's why if you're ever talking about heat, how we've been talking about heat can be evolved. It can be changed from the form of bonds into energy that's released. Therefore, heat was evolved. So that's how you used evolved in terms of chemistry. And yes, process 4 was one of the examples earlier, so it's very attentive. I'm sorry, I can't see who's actually talking, but yes, it was very attentive that yes, zinc powder and copper sulfate leads to a change in color of the solution. It's not the zinc powder itself might be one color, and then you get the zinc sulfate, which is the white powder. Okay, now I noticed quite a lot of people did say D actually, so I want to hear the thought process behind that before C.
Well, rusting is kind of just like, or at least oxidation is kind of just like burning, but really slowly. So I thought it would be exothermic.
Sorry, can you repeat that? My bad.
Rusting or oxidation is kind of the same chemical reaction as burning, except that it's way slower, right?
Yeah, in a way, there's different things involved, but we can go even simpler than that. What was our reasoning for endothermic reactions? It was that you were going to be breaking bonds, right? But in rusting, what is your product?
You're creating bonds.
Yeah.
Yeah, you're getting iron oxide. So yeah, you're right. It is sort of like burning in a way. It wouldn't be exactly right to think of them as the same, but it could be okay to call them related in this case, in the fact that, yes, they are exothermic because you are creating a bond. You actually have to release this energy so that the bonds will be formed, so that the idea for that is that these molecules will be more stable and able to create bonds rather than just blitzing around with great amounts of kinetic energy, right? You need them to be more stable to form these bonds. And so in this case, yes, the process one is exothermic. Now, one thing to make sure is that obviously rusting doesn't happen immediately like burning. But one important thing is that the speed of the reaction doesn't always translate to the other properties of the reaction. So if you do know the speed of the reaction, let's say it's some sort of thing you did in school, and then all of a sudden it's in front of you on the test, the speed of the reaction in many cases might not be exactly relevant to that point, where you have to think about the reaction. You have to think about the factors of it that you know. You know that a bond is being created. You know that energy has to be released, not absorbed. So process one is an exothermic reaction. But that leaves us with C. So I know someone typed an explanation for C. Do you mind maybe unmuting and talking about it if you're comfortable, of course, or I can just go on and say that?
I just thought that it is not a double decomposition process, and instead it is a single displacement reaction. So I thought the statement was incorrect.
Yeah, okay. So let's break it down. So what would a double decomposition be actually? We know what, oh, sorry, yeah, go.
I would believe it would be like if you had a composition A, B, C, then it would become A plus B plus C. I would think.
Yeah, we're basically on the right track. It's just rather than one compound being decomposed, it would be two compounds. I think ABC being decomposed into AB or A plus B plus C would still technically be a single decomposition. I think the double refers to it's two compounds, kind of like in double displacement, it's two compounds being displaced. So double decomposition would be AB plus CD is equal to A plus B plus C plus D. I don't know any reactions like that off the top of my head. I'm assuming it's rare. But in this case, what it's saying is that C is saying that it is an example of that, where in fact, since we were talking about the decomposition of calcium carbonate earlier, calcium carbonate is just CaCO3. You have one compound made up of three elements, but two individual groups. Ca is one and carbonate's another one. And so if it decomposes, it would be a single decomposition. Or, sorry, single displacement. Yeah, we're talking about process 4. Oh, sorry. I was looking at process 3. Zinc powder to copper sulfate. Yeah, that is not an example of a double decomposition because you have one element, not two actual compounds. Yeah, that's my bad. But you're just displacing the one sulfate and then the zinc and the copper. So your correct answer is C. Oh, what just happened to my screen sharing? Okay,
Yeah,
well,
screen sharing.
That was in fact actually the last question. Either way. So are there any questions for the end of the lesson here?
Yeah, we can bring the thank you slide still for them.
Let me bring it back up to
Okay.
I was just
Yeah. I mean, in towards the end, you saw that it got a little complex, but in the contest, that's what you would expect, that some of these questions will become, I mean, I don't know exactly what the context will say. We are not driving that, but they get a little more complex as, question increases. So
yeah, and
yeah.
In the end, it just takes this procedural thinking to get through it. I know maybe you're worried on time, but I think the learning you get from understanding these problems to the core is what's really important.
Right. And also in the contest, like having, 50-60% answer correct is considered fairly decent score.
Yeah, and I mean, get it, just doing these questions super procedurally right now is part of the practice, so that come time to the contest, you'll know the trends and such in these responses.
Will it be multiple choice?
Yeah, the question should be like this, I believe.
Yeah,
Okay.
there'll be multiple choices. Yes. So you're happy, Kavangan?
Yeah, because then you can use
Okay,
process
so I
elimination.
posted some links for the actual contest as well. You could try that. It's in the Vanda course as well, as I was explaining before. So you will see those as well. Okay, so for the next topic, by the way, folks, we'll start talking a little bit about biology and basically cell theory a little bit, which really started but from the beginning we wanted to build a little bit, and it'll get a little complex. I mean, we'll at least have 2 sessions on that topic. We'll try to get into the depth of it. I mean, most people can do physics, so we don't have enough time and resources to run all kind of sessions. So we want to focus more on chemistry side of things and the biology and kind of things where people do struggle. So we wanted to give more knowledge on those. But yeah, I mean, if I'm looking for more people, if anybody who is interested in helping, they're welcome to help, and we can run even more sessions if we get more people. And for Varun, it's very hectic, and he's just trying to find time to do it for you guys. So thank you, Varun, and thank you,
Yeah,
everybody.
no problem.
You're giving your time on the family weekend and family day long weekend, and I
Yeah.
really appreciate it. I hope you found this valuable. And let me turn my camera on too, so you guys can
Yeah,
see me.
I really enjoyed just making sure everyone's learning, and my favorite thing is everyone participating. Like sitting in the classes nowadays, online school, not a lot of people participating. It gets boring at times, but knowing people are participating, it makes it exciting for me as well.
Okay, so yeah, so we'll next session will be in 2 weeks. That's correct, Varun? I mean,
Yeah.
I need to check the dates.
Yeah, it's alternating weekends from now on. Yeah.
Yeah, so it'll be alternate weekend. So just keep in mind that you'll see more communication. Keep practicing, have fun, and yeah, and bye for now.
Wait.
Yeah.
All right. Anybody has if anybody has question, you can stay on. Okay.
Sorry, someone had a question. Yeah, go ahead.
Thank you for the class. Bye.
People are really leaving during the meeting.